All right, so last section, let's talk about power and energy. And so not a huge, I mean, it's a big concept. It's just not difficult to understand. We've been talking a lot about the flow of charge. You know, if I have a simple circuit, I'll have some charge moving around it. And charge, moves from high potential to low potential conventionally. So it goes around like this. And that movement of charge we call current. So the current moves around the circuit. Now, the thing is, we want to use some of that because we know that the charge has energy. And the kinetic, well, it's potential energy. As it's moving down, it creates some kinetic energy. And so the basic idea is, how can we harness that? How can we take the potential energy and transform that into some kind of useful energy, say like thermal energy? How can we heat things up? And how can we talk about that transfer of energy? And so that's where power comes in. Because the current carries charge, or is moving charge. And so I'm just summarizing what I just said. Is moving charge. Charge carries energy. And that leads us to power. Power, which is the change in energy over time. So the rate of change of energy over time. That's power. All right, so we can define it pretty easily. So power is the change in energy over time. And we use change in potential energy because this is all potential that the charge is carrying around. But we know that the change in potential electric energy, well, that's equal to Q times delta V. This is off your equation sheet. And so we have over delta T. But this piece right here, Q over delta T, that is equal to current. That's the change. That's the amount of charge over time. So we end up getting this nice simple equation. Power is the current times the potential difference. So there's your equation for power. The units here, if we go back here, the units for energy are going to be joules. We would get joules per second, or we could get joule volts per second. We put it all together, and this is what we get. This is a watt. So the units are watts, and we just use a big W. All right, there's some other ways that we can think about power. By the way, this is the one that shows up on your equation sheet. It's right there. So these next two that I'm going to show you, they use some of these others, and we'll do some substitution and see what other kinds of relationships we can find. Well, the relationships here make sense, right? If we increase potential difference, we are going to increase the power. If we increase the current, we increase the power. Okay, so thinking about resistors, because that's where we're going to get our change to thermal energy. So we know that the power of a resistor is going to be I times the potential difference of the resistor. And then using Ohm's law, so I equals delta V over R, we can just substitute delta V over R into this. So the power of a resistor would be delta V over R times delta V. So we get delta V squared over R. So that would be your power if you know the potential difference and the resistance. If you didn't know if you didn't know the potential difference, then we could get a new one, which is I. So we can rearrange this. Again, working from power is I delta V. That's a V. So we want to get rid of the delta V, so I can just move the R over. So I get delta V is equal to IR. and substitute that. So we get power is I times IR, and we get I squared R. That's power. So there you go. There's two other equations, but these are not on your equation sheet, so you'll need to know how to derive those to use them. But one thing you can look at here is if I graph my power versus potential energy, I end up getting that. And if I do my power versus current, I end up with the same kind of graph. So the power is dependent on the square of the potential difference and the current, which is interesting because it doesn't look like it here, right? Well, okay. So that's actually for a resistor that we would be talking about. All right. Anyway, we'll do a couple of examples. So let me get a new page up. So suppose that we had a 100 watt light bulb connected to 120 volt current. That's the current in your household. So we have 120 volt and 75 watts. We want to know, I'm sorry, that's the potential difference. We want to know what the current is. So this is in watts, so that's power. So my power is going to be 75 watts. And so this is how we rate bulbs. It's how much power can they output for the given voltage. And they're usually, in the United States, it's going to be rated at 120 volts. Actually, I think in all of North America. If you go to other countries, this will jump up. We could get 220. All right, so anyway, power is current times the potential difference. So we want the current, so we would just divide. The current is going to be the power divided by the potential difference. So we get 75 divided by 120. And you get, 0.63 amps. And most household electronics are going to be less than an amp. Let me see, let's get another one. How about this? How much power? So we're going to have a 60 watt bulb. Man, my last bulb was really good. I'm going to start over. It kind of looks like a skull. All right, so the power of this thing is 60 watts. It's rated for 60 watts, but that power, remember, is rated at 120 volts. Okay, so we connected it to a dimmer switch, and when we dim it down, and when you do that, what you're doing is you're just decreasing the potential difference. So we decrease it to 100 volts. And so now we want to know what's the actual power. So what's the power usage here? So it's rated for 60 at 120, but we're only putting 100 through it. So what's the new power? So to get this, what we can do is we can determine the resistance of this thing. So power is I delta V. So this doesn't help. So I don't know the current. I know the potential difference, which is at 120 volts, I would get a power of 60. So I could figure out the current, but that's not going to help me because that's at 120 volts. What I want to know is the resistance. So we can use delta V over R. And if I rearrange this, no, I want to leave it like that. So we'll just substitute. So P is going to be delta V over R times delta V. So we get potential squared over R. You get power. Flip these, so the resistance is going to be the potential difference squared divided by R. And this is using the original values, these. So it's 120 squared. I'm sorry, this was power. Making all kinds of mistakes. Sorry. And then 60 for the watts. So we get 240 ohms. That's the resistance. And now we can use the same equation, except now we'll use it for 100 volts. So the power is going to be the potential difference squared over the resistance. The potential difference is 100 volts squared divided by the resistance, 240. And we get a power output of 42 watts. And that makes sense. We reduce the potential difference, so the power should decrease. And it does. We get less light, right? Instead of being like this, it's like that. All right. So there you go. That's power and energy. That wraps up this entire level. You'll do some practice. It'll probably be a short practice. There's not much to this. And then an assessment. We might have a quick, like a level total assessment, and then we need to start circuits. That way you can build your house.